I don't know if the setup was gonna work as expected, because I've done, so this is a new machine and I'm setting things up and I only have 20 minutes, but it is what it is. Okay, if I don't just do that, I won't ever do it. Like, it's I think it's a problem, when you have tight schedules. Like, it's just difficult to stick to these, and I haven't really been recording for almost a month now, and it sucks because I want to keep going with these. I've been trying to solve problems on Twitter. Yeah, sometimes I feel like it doesn't capture the whole thing as good as in a live stream, because ultimately what I want to do is be able to capture the learning process better, right? That is really what I want to do with these, and so I've been finishing problem 1.1 via Twitter threads, and so you can go in Twitter and look for them and find them. So what I want to do now is want to move to the second problem, the free particle. So the second section, and approach problem 2.1, and at least now do an initial, because I don't have much time today, but at least I want to do that first initial mental breakdown of like, what does the problem look like, and how can we approach the problem without looking at the solution if possible. So we will just focus on the, I'll just put it, come on, what have I done? So I'll just focus on the, I'll not look at these, we'll just stick to these, zoom it in, and I think that is it. Yeah, exactly. So let's see, problem 2.1, and as I said, like, yeah, well, we'll see. Anyway, I don't want to talk too much because I don't have too much time anyway. So problem 2.1, a free particle is initially at T1. So we're talking free particle. And you know what? I should actually open up an incognito. So free particle, C, what that, because there's, yeah, okay, that's basically, the initial state is described by this wave function. I hope the sound is coming through well, so we'll see. And so alpha is a real parameter, and then I guess R is the radius, and so this is the R observable, so it's whatever we're using for position, I guess. Compute the normalization factor n. I guess this is just going to be pure math, right? So this is just going to be, I want to try one thing, because I know, so Twitch Studio has this drawing over kind of thing, and I've been wondering, like, if I go into draw mode, like, do you guys, I have the pen on the second screen, okay, but like, do you guys see that? Probably you see that. Okay, but I'll just clear the drawings. I don't know if that slows down the thing. But basically, this is just going to be something as basic as like, my guess. Okay, so we'll try to do a guess. Let's open Paint, and let's try to do a guess for all this kind of stuff, which is basically the normalization factor. I guess that just means that if I do the integral of like this wave function, right? I guess through time? No, I don't know if it's like through time or through X, to be honest. No, because I think it's through X or R, whatever it is. So, but that's just a detail. So if you do the integral, right, it's 1. Remember that that's the point, right? So of that square, sorry, that square, because we want is the probability density function to add up to 1, so all the area below the density function to be 1. I think that is going to be how we solve A. How we solve B. Show that the probability density of finding the particle with momentum is isotropic. It does not depend on the direction of the momentum. Cool. So isotropism appears again, and we're talking about momentum, but we have something that is position based. So I guess here, as a kind of a just thinking about how to break down this problem, what I would usually do here is that, okay, so I know those are, so momentum and position, they are basically as far as I know, non-commutable, which means that if you measure one, you can't measure the other. And so you actually have to apply a transformation to do that, right? And so we probably need to just first transform this into the momentum basis and then do the actual probability density function, sort of the squared thing, right? And then we have to prove that that function is isotropic. And I think that meant from the previous exercise that it just depends only on the distance to the origin of your coordinate system. So it does not depend on what direction we're going left or right and stuff like that. But how do we do this? So how do we do, just quickly, how do we free particle switch basis? Would you do like that? Switch to or transform to momentum wave function or something like that. Or something like this. Why am I getting? Okay. So I guess that's the free particle momentum space. Momentum, yeah, I think that's what we have to do, right? Okay, so it's similar to these. So you have find the momentum space wave equation for the free particle in terms of whatever that is, and it is defined a 1D position space. Okay, so you have to do a Fourier transform. Is that what it is? How to transform between position and momentum wave function. Representations, eigenstates. Is the audio gonna come through to you guys? Because I don't know if it's going through here. Looks like, but I don't see.
So, to now try to bring it all together, we've started talking about free particles. We talked a bit about momentum eigenstates. There were now some Fourier transforms. Let's.
Okay, but that's just introducing.
Pull some.
I guess I just have to find a way to tweak the sounds in here. Yeah, speakers. There's no sound settings. Speakers. The speaker I want on my computer. Yeah.
Threads together.
Yeah.
So first, we have our momentum eigenstates. These satisfy the idea of saying that my momentum operator applied to this function will give me the momentum of that function times that function back. But now notice that we're writing this as a function of position. That this is saying, well, what does that look like in position?
So this is just saying if you apply the momentum operator, it's gonna still give you, because I thought that give you is the momentum times the wave function. Maybe I should just let me start from the beginning.
So to now try to bring it all together, we've started talking about free particles. We talked a bit about momentum eigenstates. There were now some Fourier transforms. Let's pull some threads together. So first, we have our momentum eigenstates. These satisfy the idea of saying that my momentum operator applied to this function will give me the momentum as a position space. And you could imagine this as basically saying, okay, I have position. What does this look like? Some sort of wave. Cool. But now there's a different way we could write this. And we could instead think about, well, what is this?
Yeah.
What is my wave function
That's what I want to
expressed in position space.
Yeah.
What that means
in momentum space, that's what I want.
Is now my horizontal axis is not going to be position, it's going to be momentum. And so what would that look like? Well, so let's call this now, right? If it's but like video, then that would equal back. Now notice that I've now written it this way, that I'm not saying necessarily what my form is here, but I could still have a momentum eigenstate that has a very specific value of momentum. And I'm calling that fancy P. So what that means is that at that value of momentum, I have my thing. This is basically a delta function. And everywhere else it's zero. The only value of momentum it has is that. So this actually gets to be the idea of a Fourier transform. So there is basically one specific wavelength, wave number, frequency, whatever you want to call it here, and one value here. And so it can be really helpful to actually think about our wave functions in momentum space. What that means is this, like what energy, okay, and I say, oh, my wave function is this. Well, notice that if these are equal, that's then the superposition of a wave going, it's actually going to be, just keep in mind what's up as a sum of our eigen.
So it seems it's going to be the way that a Fourier transform, that's what it seems like it's got to be. Express wave function in momentum space. It's complementary. Yeah. Suppose if we know the wave function initial time t of function related time for solving such problem, first find is the initial wave function in momentum space, which we find by using the inverse Fourier transform. But why? That's an interesting question. Why is it the inverse Fourier transform? Okay, but anyway, that's not like let's not get stuck. So, but that's just I'm just trying to fly through the problem first. Okay, trying to fly through the problem first. So this means that for solving B, we'll first have to apply the inverse Fourier transform, get the momentum space thingy here, and then do the and then do the probability density function in momentum space, and then try to find the probability with the specific momentum, which is kind of either going to be 0 or something, right? Because I'm assuming as you could see in the video, right? Because they are complementary. Like if in just position space is something oscillating, which it looks like, right? Because it's of this form n times, and then there's this e thing, and okay, this is real, so we know it's not imaginary, but it's like, if you see an e to something, it's definitely something that's oscillating. Okay, but it's oscillating if there's a complex exponent, right? And that's just a time 0, right? So the general expression would still change a bit, but okay, yeah. But if it's like that, then if it's complementary, for like I don't know really why that works. I don't know why the inverse Fourier transform is actually the one that we're looking for, but it literally means that, you know, that is just kind of like peaks somewhere, right? Which is basically you could think of them as the frequencies that make these thing here, because that's what the Fourier transform, inverse Fourier transform thing does, right? So it goes from the frequency domain to the what's it called, to the periodic domain, right? So, but I don't know why that works. Is it because it just happens that this pair of observables is complementary, and so this just means that that's the way it is? I don't know. This is something to definitely research later on, but that's how I would approach B. C, show that the spatial probability density is also isotropic. Okay, so in this case, I guess built upon these, I'd find the normalization factor n, although probably can do that without these, and then compute that squared. It's not squared right only, right? But it's like, yeah, I mean, that should even be fairly easy to do, right? Because it's like, so we know we know that it's like the the complex conjugate times itself, but because we're talking about like something in this form and we know this is real, then literally this actually is just these, right? And so this is like it's gonna have, well, we know that e to the power of whatever something here, right? It's always like you can express it with like a sinus of something and like a cosinus of something. Like it's something that like oscillates in a way, and so that's why it's isotropic probably, because it doesn't matter what you're doing. It's really literally the distance to the origin that defines what what your position is. Just as a wild first guess, okay? And I've got like 5 more minutes. I'm just trying to break down this problem at least. So this is for sure these, and then these calculate the expectation values. Okay, this is gonna be interesting because I've never really done that on paper, like with just math. And this is the momentum and position. It's an operation. I just don't know. Is it the? How do you do that? So basically, calculate expectation value of wave function. Okay, so it's a formula. So it's an integral. Okay, so it's the integral of the. Yeah, okay. So there is, again, it's like, but it's from the probability density function. So you do an integration. But there's got to be something, you can't just integrate. There's something more to it, but okay. Yeah, there's some derivative, second derivative. Okay, interesting. I don't know. With the x in between. Okay, but it's an integration. So this is again just but it will be interesting to know why, right? So why are these specific things like that? Why does this work as a module, like as a model? Like, remember that I'm trying to understand just also beyond the pure math, right? But that's basically how you do it, and you do that, and then show the expectation value of r squared increases with time. It satisfies this inequality. Like r squared, I guess this is, I don't know why r squared. You do r squared. Why would you do r squared? I guess to get, yeah, okay. I guess you do that to get rid of the negativity. So like just because that's just the one dimension, right? So we're talking about like one dimension. That's whatever the radius or the distance to the center of your coordinate system, and so you would want to check that the r squared grows, or like you're just analyzing how that works with respect to both like the left and the right side of things. It's expectation value again, and then modify the initial wave function, assuming that initially the particle is in the state described like that. Calculate the expectation value for this case. So now we're doing something. Okay, so now we're adding a complex part to it, and then we will and then we're going to do some integral, which is not going to be nice, because an integral of complex things means shitty contour crap stuff, whatever. I don't know what's that called, but it's complicated integration. But okay, that doesn't seem like there's a lot new in here, other than me learning about the I want to get out of this exercise to learn more about sort of the position and the momentum spaces, and then why does the inverse Fourier transform actually work as a way to translate between these two. I know that they don't commute. This means you cannot like measure one and the other at the same time or something like that. And then expectation value. So this is just fairly, I think, useful basic tools, right? Changing bases and doing expectation value stuff. So far, nothing super new, but let's see. Cool. So I'll really try to ramp up the streaming again and then get going with these one by one. Today I just wanted to do like a quick breakdown and approach to that exercise. And then we're doing later on, hopefully in the next week or two, we're doing simple potentials, which I don't know what that is. We're talking about like particle in the box and stuff like that, maybe different models already here. angle of reflection. What the hell? Okay, we're doing probability current densities again, so that's definitely not useless. Anyway, let's see how much we can do without looking at the solutions. See you next time.